Hi guys, welcome to my channel. Today we will be designing finite state machines using Verilog. So what is a finite state machine? A finite state machine consists of a state registers and two blocks of combination logic to compute next state and the output given the current state and input. Okay, so basically why we saying finite state machine, because this machine will contain finite number of states. That is, if the machine contains 4 states, it will contain 4 states only. It won't contain 5 states otherwise. So to proceed with the development of finite state machine, let's design a divide by 4 finite state machine. So it will have input clock, reset, okay, and let's say we have an output y, and output y is 1. Okay, only when uh, the state machine reaches state 0. Okay, and the state we need to like declare two variables. uh, they should be declared as rest, okay, because we'll use them in our always statement, and the two variables will be the current state and the next state. So let me write that, and the state encoding that will be use is of 2 bits, so let us encode it using 2 bits. um, so state and next state. Okay, and let's now start with the state encoding. For state encoding we'll use the parameter variable. Parameter keyword you can usually use as internal keyword, and usually it remains constant. So let's encode as 0, state 0, which is also known as the reset state, to 0 0, 2 bit, the 2 bit 0 0, parameter s1, 2 bit 0 1, parameter s2, 1 0, and parameter s3, 1 1. Okay, so now here comes the logic for state and net state at positive edge of clock. So we'll have an always statement here, always at the rate POSH clock or POSH reset. And during reset we want the state to be reset to state 0. So we'll also have POSH reset in our sensitive list. Okay. So inside the always statement we'll have if reset is on. Okay, I want my state to be as 0. Okay, otherwise if reset is not on, then state should be assigned next state. Now the logic for the next state, will design it as combinational logic. So next part comes combinational logic. So we'll again use the always statement for this case, always, and for combinational logic you need to use always at the rate star. Okay, we'll write the case statement, case state. Okay, and end case also. Okay, so if my state is S0, next state should be automatically what? Next state should be S1. Okay, if my state is S1, next state should be S2, and if my state is S2, then next state should be S3, and so on. It the cycle should repeat. Okay, if the state is S3, next state should be S0. It is in cyclic fashion. Okay, this is done now, and by default state should be next state must be S0. Okay, now combination logic and logic for state and next state is completed. This both always statement, they always run in parallel. Okay, so this always statement will be executed concurrently, and we want our y to be 1. Okay, so I'll use the blocking assignment for y should be 1 whenever the current state is equal to S0. Okay. So basically what we are doing is that on every clock pulse we are having 4 states. Okay, so it's nothing but divide by 4 FSM. Okay, so if frequency of clock is f clock, if f clock is the frequency of the clock, then frequency of output y shall be 4 times f clock. Okay, and time period, not 4 times actually, f clock by 4, because it is divided by 4 FSM. Time period must be 4 times t clock. Okay, let's save this. Okay, now it is saved, and let us check for any syntax error. Okay, no errors and warnings, and also no infos. Okay, we can proceed with RTO schematic now. It produced a different schematic actually. Okay, the file was not selected, correct. Okay, save this file now. Check syntax. RTL schematic. Yeah. So now this is the divide by 4 schematic here. Divide by 4 FSM. It takes input clock and reset and produces output Y. Nothing but It consists of an FSM machine inside. So by default, this is the basic unit here, and it cannot be seen more deeper. Okay, so it is using an FSM memory inside with state logic. And now we can proceed with writing test bench for FSM to check if our logic is correct or not. We can like create a new file for this new source. Let's write FSM4 test bench. Okay, and input shall be declared as reg. Okay, reg clock reset. Output is a wire, so wire and divide by 4. Device under test. Clock reset and output wire. Okay, and now we'll have a clock generation logic. So always begin and end CLK is equal to 0. Ten nanoseconds. Clock is equal to 1 for 10 nanoseconds. So what is the time period of this clock? T clock is nothing but 20 nanoseconds. Okay. Now clock logic is completed. We'll write the test cases using initial begin statement. Okay, let reset be equal to 1 so that initial state is reset for some 5 nanoseconds. And after that reset is off. Okay. Now our test bench for the FSM is complete. We can proceed with simulation. So you see like automatically the instance is hierarchical instance is created here. So yeah, we can proceed with simulation. Just click on simulation tab. Check for any errors if present. And simulate behavioral model. Okay, the behavioral model is now simulated. And this is the output. You may press scroll plus control down. Okay, so that you can zoom out the view. Okay, you see like this is the output Y. We can drag it below the clock for better understanding, or yeah, let it be above the clock itself. Okay, you see like my state when my state is 0 0, okay, output is 0 for this period. During this period state is 0. For this period next state, which is the next clock cycle, state is S1. Next state is S3. Then again it is S0. It begins with S0, S1, next period S2, S3 and S0 again. So you can check the time period of this also. This is starting on 70 nanoseconds and ending on 150 nanoseconds. So 150 minus 70 is 80 nanoseconds, which is equal to 4 times of clock period. Clock period is 20 nanoseconds. 80 minus 100 nanoseconds is 20 nanoseconds, and 80 into 4, 20 into 4, okay, 80 nanoseconds is the clock period of y, time period of y actually. So frequency is also decreased by 4, divided by 4 actually. So this is how we design a state machine, and the state machine that I have designed is actually sequential state, but not necessary actually. You may have state S1, next state as S2, and state is S0, and so on. Like well, different combinations can be there, but like the test bench will remain always same. You may like modify this logic also a little bit, and also the combinational logic in the end also can be different. So this is how we design FSM in Verilog. Let me know if you have any doubts in comment section.